50 almost. Okay, so I must say good morning to all of you. And then I thank at the outset the organizers of this AICT IST FDP on artificial intelligence for and its application in biomedical engineering. And Dr. Swati Bisikar, who was in contact with me, we decided mutually to talk something about linear classifiers for machine learning. But I've taken a liberty to tweak with the title of my session, and it is pattern recognition or classification, a cursory review, concerns and issues. I have taken that liberty and freedom on my account to change the title. The contents are more or less same. We'll be talking of linear classifiers for machine learning. Okay, but the title is bit changed here. And because in such FDPs, the speakers don't know what is a demography of the audience, you come from which backgrounds and all. Therefore, I generally keep the such sessions quite light. So I have started, there is a 60 slides presentation I have made for this purpose. It is compiled, collated information from web or whatever references I generally refer to. But then it is quite a shallow presentation, a surface level presentation, which will be simply apprising the audience about classifiers, linear classifiers, which are used to recognize or classify the patterns in the signals will more remain signal centric rather than data centric. Even though both are same, signals today means data. Okay, and therefore we are today completely engrossed in the words like artificial intelligence or neural network for that sake, in the machine learning algorithms, the deep learning and lots of networks, and above all the data analytics. All of these terms and domains, they overlap. All of us know that they overlap, right? Machine learning is subset of algorithms which are used in artificial intelligence and so on. And the neural network is one of the techniques to tackle classification problem. And today's buzz of machine learning, IoT and data analytics has made us to think about all this very, very seriously. But I must make a comment to begin with that it is all really an old theory. We require all old theory. Signal processing theory, we require a lot. Certainly, we require a lot. We require a lot of inputs and knowledge of mathematics, in particular linear algebra. Okay, that we need a lot because we have to deal with all vectors, matrices. Okay, and then we certainly need knowledge of optimization theory. Okay, take it from me, it is optimization theory. So machine learning or data analytics needs a lot of the things from optimization theory, from linear algebra, and certainly above all probability theory, stochastic signals theory, right? That is something which is required as a prerequisite to tackle the domain of machine learning and this pattern recognition, classification, etc. And then those who have started learning machine learning as a domain, as a course, or you have started teaching it because it's a buzz of the today. Okay, we are into the era of machine learning and AI and data analytics. So some teachers on their own motivation, they have started learning and teaching these courses on machine learning, right? For them also, what I suggest is that we should have a prerequisite knowledge of linear algebra, probability theory, and optimization. These three are required for the sake of that, right? As I already mentioned, I have all pushed the mathematics in this total presentation towards the end slides. I'll try to see to it that you get some kind of notion about Bayesian decision theory, which is one of the classical classifiers, used as linear classifiers in the total machine learning classification problem. And then I've also tried to incorporate the decision tree structure based classification, which is now sidetracked, but it is used in machine learning also. And then ultimately the support vector machines. Okay, so actually whatever algorithms you used in machine learning, I have sidetracked them. Okay, so truly speaking, it is a predecessor of machine learning. So excuse me for that, but probably I thought that this happens to be an AI course. So majority of the speakers will speak about machine learning approaches and ANN approaches towards biomedical signals. So I said, let us keep them on some other track, okay? And just apprise the audience about the predecessors which are not still obsolete. Bayesian decision theory or classifiers are still not obsolete. NB classifiers, naive-Bayes classifiers are not at all obsolete today. Okay, SVM is not at all obsolete today. Feature extraction is not at all obsolete today. It is still existing. So let me apprise you on that. But the treatment happens to be lighter. It's a shallow surface level presentation. So I assume zero knowledge from the background any zero background knowledge from the audience. So you have to simply keep listen to me. In online education, we understand, we are all teachers, that there are a lot of limitations. I cannot check whether you understood my content delivery or not. I cannot look into your eyes. I cannot look at your faces. And therefore, there are a lot of limitations in online virtual learning. Okay. And I assume that all the audience is sincere, and then they are eager to listen to me because they'll get something out of it. Those who already practiced machine learning, those who already practiced pattern classification, they'll get this to be a bit boring because the treatment is quite fundamental. Treatment of session is quite fundamental. Okay. And they'll feel a repetition, but sometimes to listen to revision or recapitulation is also an enjoyment. So for those who are already practicing, learning machine learning for their sake, for some their own, out of their own motivation, or for their teaching learning, they should excuse me because for them it's just a repetition. Okay. So I'm assuming zero background knowledge from the audience because the presentation is shallow, quite shallow. So I may please be excused for that, right? All the fundamental terms are being again revised over here. But as I already said, revision is sometimes pleasant for all of us. It also re-endorses our concepts about whatever we could understand, right? And in the AICT FDPs, I typically make it a point that teachers should also learn to freshen up, refresh their fundamentals. Okay. So generally in FDPs, I teach quite fundamental, not advanced. Okay. And therefore you need you have a lot of advanced knowledge, but the fundamentally, if you are clear, understood everything, then you can really build your building upon those fundamentals. So treatment of this total session is fundamental. So please bear with me for that. Those are pundits of machine learning. Okay. Or they can even leave the meeting. There is no issue at all about it. Okay. So I have tweaked with the title. It is certainly linear classifiers for machine learning, but it is a predecessor for machine learning, so-called authenticator algorithms. Okay. It's all prior to what is happening in machine learning today. Okay. So I'll take all that meta pattern recognition or classification as a problem. A cursory review of all of that. But there are many of the slides are ending at question marks. Okay. So that became an open issue. Why did machine learning evolve from the classical topic of pattern classification? Okay. We had a very classical book titled Duda. He has wrote a nice book which is widely accepted throughout the global community of researchers, Pattern Classification by Duda. Okay, that book many of you will be knowing. So this all material is derived from Duda's book anyway. But then every slide typically ends with concerns and issues, question marks. And those question marks are indicative of what we have to do tomorrow. Okay, what are the probable research areas where we have to get tuned with the optimal classifier and then feature set and all that process of classification, right? So I have taken that liberty to change the title, and accordingly I'll go. There is 60 slides in all, and I'll try to make it up to 115, which is the time given to me. Okay. Pattern recognition or classification. Probably all of you know, machine learning typically aims at two applications. Which are they? One is classification, other is regression. Classification typically is a discrete output kind of application, wherein I have to say to it that I have to assign an object or an event. Object typically is a feature, or let's say entity, which I can draw from image or picture or speech or audio or temperature or whatever, like what are signals we come across. Okay, so objects can be drawn from that. There are the patterns which can be drawn from that. Whereas event typically is an entity which I can associate with video, because in video I have motion activity. Activity is going on, so event is going on. Okay, and pattern can be therefore defined as an object in an image or a speech or audio or whatever. Okay, it is all in the signals. Patterns are available in the signal, and event is typically concerned with the live ongoing activity. Like speech is real time, or images, photographs are real time going into video. Then that is a pattern. Okay, so pattern is either an object or an activity or an event, and I have to attach to that object its recognition. How do we attach the recognition? By out of several known categories or classes, I attach a class label. Okay, and these all class labels, categories are discrete naturally. In this picture, it has been shown there is a set of data, literals, capital letters A and B, which are handwritten typically, and there are two categories a priori defined: category A, category B. And what is the classifier's job? What is the pattern classification job? There are two patterns identified, A and B, and I'll be attaching the label category A to all those A's. I'll attach a label category B to all those B's. So I have certain predefined number of discrete categories or classes available. What is the output therefore? A class category label. What is the input? Pattern, which is either an object or an event. right? And believe me, it is a universal phenomenon. In case of regression application, we are going to find out output which is not discrete, which can be continuous. It can have kind of a finite word kind of stuff, and then it can be represented in terms of floating point number. No direct categories, discrete numbers over here, right? So regression is typically different, but ultimately mathematically it boils down to same. We'll be restricting our discussion to classification task, okay, and that to classification of patterns, and patterns means objects otherwise or events in the video. Okay, I have got a priori defined, higher defined categories or class labels. I have to attach those class labels, and there is an intelligence involved in this all classification recognition process. Recognition is same as classification, though no issues, right? There have been two confusing terms, classification versus clustering. Clustering is also known as unsupervised classification or unsupervised learning. By the way, learning is a word which today goes with synonymous with classification, right? Actually, humans learn, machines learn. What do they learn? They do learn two things, either a classification or regression. So when I say supervised learning, it means supervised classification or supervised regression. That's the meaning of it. Regression is finding out dependency between variables and predicting the value of output variable. Okay, classification is attaching a class label to a pattern or object or event. That's the way, right? Supervised means the categories, the discrete class labels are known to me beforehand, a priori. Okay, and again the example is there were two sets of elements with me, data with me, samples with me, whatever you say, whatever patterns with me, A and B, and I could attach a label because which was a priori known, beforehand known, category A, category B. Clustering is the one in which such a priori class label knowledge is not available to me. It is not visible to me. It is not available to me at all. So what I'll do, I'll just scan the pattern. Pattern is with me, and there is a one numeral one over here, and there is a straight line. Okay, slanting line and straight line, and therefore I can just categorize without a priori knowledge of class labels. I've just grouped them. All the ones are grouped together and all the lines are being grouped together. It is known as clustering. Okay. So I've got terms like supervised classification or regression, unsupervised classification or regression. Okay. We are going to ignore again unsupervised stuff over here. Only just are going to consider in the presentation supervised classification or supervised learning, which happens to be classification is a really a tough task, right? Humans do it very easily, but machines will take a long route to attain this classification task, right? But the machine learning is a way to therefore do it in a very faster manner and very efficient manner, right? That's the way. What is a pattern? So I said pattern can be object or event, right? Object is typically in the image, events are typically in the videos. Let's say we have shown both the examples over here. What do we do? But typically mathematically, representation wise, I am going to represent a pattern by a set of numbers. Set of numbers is a vector. Is it not? Vector is a matrix, submatrix, either a column vector or a row vector. So I got capital X, and capital X contains elements x1, x2, x3, xn, etc. So pattern, object, event, synonymous. They're represented in mathematics by a set of numbers, which is either a row vector or a column vector, right? Row vector, column vectors are transposes of each other. There is no issue therefore. So vector means sub matrix, right? We understand that. Either a column matrix or row matrix, and it has got n elements over there. This x1 to xn, they typically describe the pattern, describe the object, represent the event. They truly stand for, that object. Okay, and therefore sometimes this x1, x2, x3, x4, no, they are known as attributes, characteristics, properties, or more generally features of the object, features of the pattern, features of the event. Feature is a more scientific word in connection with image processing, video processing, and now machine learning. Okay, so x1 to xn happen to be n features of that x. What is x? X is a pattern. Okay, so we'll be carrying out this kind of notation in the future, this also, presentation also. We have shown biometric pattern, a thumb impression over here, then an eye over here, just to find out iris or probably any other part of the eye. Then an EEG signal is over here, a palm print is over there, a face is over there, signature is over there. All these are having patterns, is it not? And a certain pattern I want to really detect, recognize, and attach it to a class, let's say. I have to attach it to a class. Let's say I want to recognize face. Face has eyes and eyebrows and nose and lips and ears and then hair and etc. These are all predefined, a priori defined class labels. And I can then say that this typically belongs to a nose class. A particular pattern of this I'll identify and it belongs to a nose class. I can certainly do that, right? John Smith, this is the character recognition problem, character classification problem. I can do that, certainly. This is a video in which that person is going to just move his hands up and down. And there are some hand gesture patterns, which are video patterns, actually, events, therefore. Activities are there. This is also a pattern. Okay. All such patterns can be classified, attached with the label in a supervised manner. Our emphasis on supervised learning now, supervised classification now, therefore a priori defined classes over there, right? That we have to do. But what is a pattern? It also, today we are into this all huge domain of classifying, retrieving, identifying, etc. Let's give some real life applications. I have applied for a loan or credit card to my bank. And what bank change? What bank checks? They they ask me for some information. Income, percentage of income of mine, percentage of number of dependents on me, mortgage amount, etc. They ask such kind of data with me. Okay. And they have to scrutinize my application for loan or credit card, right? And they have to naturally put me in a category, whether I am credit worthy or not credit worthy, whether I can be allotted a loan or not, whether I can be allotted a credit card or not. Decision is therefore binary. Yes or no. Loan yes, loan no. Okay. And there are a lot of features of that application. Which are they? Income, number of dependents, mortgage amount. These are really real life features or attributes which they'll be using as an input to scrutinize my application, and they'll decide. What is the decision? Classification. What is that? Loan yes, loan no. Credit card yes, credit card no. Only binary decisions are over there. Okay. So classifier is an intelligent algorithm which does this task, which analyzes all these inputs over here: income, number of dependents, mortgage amount, for a loan or credit card application. Matrimonial services, it has become a big business now. No relatives are going to intervene or interfere in the marriage business. Okay. What we do, therefore, the bride and groom prospective, they just simply enroll on some matrimonial services web portals. Okay. Then they input the data: age, personality, looks, hobbies, income, and everything, and so on. Based on that parameter, there is a desirability classification, right? No, the prospective groom may search for a bride and he can say desirability, yes or no. I have selected this for me or not as a partner. So there is a yes, no kind of decision again. It's a decision. Classification is a decision. Maybe binary or maybe in another number of Emery labels. But let's say binary for the sake of simplicity. So desirability classification. Web documents, I search on Google. So I just attach keyword-based descriptions. Let's say football or NFL. And I'll get all those classified documents with me on Google. Let's say football. So again, whether related to football, I get classification or not. Yes, I get that. So all these happen to be real life applications for me. What is a class? Class is a category. It's a collection of similar objects. It's very easy to understand. I have here images of males and females. Okay. So female is a known class a priori. Male is another known class a priori. Right. There are two classes. And then looking at any new face which is coming to a face recognition system, a face classifier system, I can simply put the incoming face into these two classes. Okay. So face recognition system is a classifier, whether linear or nonlinear, we'll come to it. Okay. It's a classifier which will simply put a new face, recognize it, do some processing, and will see to it that I can put it in one bucket. Which is the bucket? Either a female class or the male class. That's the job of a classifier, really. What are objectives of classification? Goals of classification? There are two goals. Both goals are really very intelligent. Humans can do it quickly, but machines will learn it and then do it. Okay? It will learn it and then do it. But once machines learn it, then they can really chunk huge amount of data beyond humans' capacity. Right? We can classify to the limited extent. Nature has given us limited capability, but machines can be trained or made learned to have infinite capacity to drive the classification problem. Right? What are objectives of classification? Separate the data belonging to different classes. That I have to do first. I have sample points, I have data, I have images, I have photographs, I have speech samples, whatever. Everything is now vector for me, right? Vector of data, feature vector with me for that sake. So input to typical classification problem system is a feature vector, x1, x2, x3, xn. That capital X, I showed you the vertical vector over there, right? And that vector is the input. Okay. But I have to see to it beforehand. I have to make some sort of pre-processing and see to it that I can wisely separate distinctly separate the data belonging to different classes. And there starts the issue number one. I can have these features coming out of from classes which are quite confusing, quite overlapping. We're going to address those issues in the future slides, right? I have to separate the data belonging to different classes. That's a job number one. I have to find out decision boundary, hyperplanes. These are all terminologies of machine learning, right? I have to find out decision boundary very correctly. I have to find out or sketch hyperplane very, very correctly. Okay, and see to it that I can separate the data belonging to different classes. More number of classes, problem becomes more complex. Only binary classes, two classes, yes, no, plus one, minus one, like that. Only two classes. Problem is relatively simple. Given new data, I have to do first job is what? Therefore, different classes, separate the data. Data belonging to different classes, right? And second important problem is given new data, similar data, assign them to the correct category. I have a priori before and defined the classes. I already separated the data. I have trained the system. After training and learning, I want to test it for the given new data, assign them to the correct category. It's a gender classification system is my algorithm of classifier. Okay, given a new data of the same type, same face, I have to simply categorize it into two known classes, male and female. That's the way. Becoming more mathematical, main approaches are like that. Omega 1, look at the right hand corner. Female faces are on one side and male faces are on the other side. And there is a boundary which I have shown. That boundary is certainly non-linear. Certainly non-linear, right? Omega 1, you will find omega 1 as a label over there. Omega 1 is a female class label, or class label omega 1 means female. Class label omega 2 means male. That's the meaning of it. Okay. What does classification or classifier or classification system or algorithm does? X is the input vector, which is pattern, standing for pattern. Typically for us, feature vector, attribute, characteristic, property vector. That's the way. Okay. X1 to Xn. What does this algorithm do? Classifier do? It is simply attaching to that pattern, that feature vector, based on the features, based on the data. It simply assigns omega, a class label. That's the problem, right? No. That's the problem. I've got two classes, omega 1, omega 2. So job is to attach with that input vector X, either omega 1 or omega 2. I have multiple classes, omega 1, omega 2, omega 3, omega 4. Then I have to look at the new pattern and see to it that I'm going to apply that to attached with the label of omega 1 to omega 4, whatever, right? There are two approaches mainly. All statistical approaches, machine learning typically falls under statistical approaches. Okay, and therefore it is sometimes mixed, sometimes distinctive. So generative approach is what? It is purely statistical, which I'm going to talk today. Okay, generative algorithmic approach is what? See, there is a probability. Every time there is probability, no, classification business is probability business. I'll be classifying the face, probably let's say incorrectly. There is a female who has all the makeup on her face, which will make her look like a male, or otherwise other way around, let's say. Okay, so that can be misclassified also. Okay, probability of correct classification or probability of erroneous classification. There is a probability. Okay, and therefore the probability theory business enters heavily into classification. Remember that. What I have to do? What is generative model doing? It models directly. It models directly the joint probability of occurrence. Okay, joint probability density, or probably the distribution function. Small p is a distribution function, probability distribution function, joint probability distribution function. It is joint of what? Joint of X and omega. X is an input vector to me, input vector which stands for feature vectors for particular pattern, and omega is a class assigned to it. Is it not? So I have got therefore a joint probability density or distribution function, small p, as a function of X omega. Joint occurrence, right? This X has to be coupled jointly with this omega. That's the way, right? And modeling probability distribution functions is a tough task. I have to assume the underlying probability distribution, generally it's a normal distribution, Gaussian distribution. I have to assume them, okay? And make the predictions about the new face coming in, about the new X coming in, and assigning it to the new class using the very, very fundamental Bayesian rule, Bayes rule, to calculate the probability, conditional probability of given the input vector X, what is the class omega? How do I define it? P in a bracket, omega conditional X means what? The X input has been given, it has occurred, X vector has occurred as a pattern, as a feature vector at the input of the classifier. What is the job? I have to assign omega to it. And there is a probability. It is the why probability? I may be 100% correct. So x belongs to omega. Let's say x1 belongs to omega 1 class. So probability of omega 1 oblique x1 could be very, very large, 100% almost. But it is a probability. I may go sometimes 0.1% wrong also. P of omega 1 upon x1. Let's say x1 belongs to omega 1 class. Then probability of omega 1 conditional to x1 could be 0.99. But it is still an inaccuracy embedded in system of 0.1. Is it not 0.01? That is still there. All it's a probability business. This is generative model. Okay. All classical linear classifying models are generative models. They typically play with the knowledge of probability theory, Bayesian theory, lot of Bayesian theory, Markov random fields, Markov chains. There are a lot of stuff over there. I'll come to that. Okay. And remember me, this pattern classification, machine learning, data analytics is a serious mathematical business. Those who have started learning it, they must have realized it's a serious mathematical business. You have to have a sound knowledge of probability theory, linear algebra, and optimization theory. You must have that. Okay. Then only we can confidently learn. It is not only skill. It is very classical philosophy. Python for machine learning could be a skill. But then to have in-depth knowledge of machine learning certainly requires a lot of mathematics. You realize it. Okay. In case of discriminative algorithmic approach, we do not need to model probability. Do not. Okay. We will be giving the decision about whether x belongs to omega, x1 belongs to omega 1 class or not. Just by learning a direct mapping from x to, there is a lookup table, direct mapping from x to omega. Okay. And that is something which is discriminative model. People say machine learning classifiers are typically fall into discriminative class, right? They are intelligently bypassing probability theory and they have therefore jumped into a more fast way of implementing the classification as an issue, as a system. Okay. Final output is same. Pick the most likely class label omega. Most likely. Is it not? I'm going to collect the features and I have a assurance, some confidence, in the interval, some confidence that this x must be belonging to this omega, right? That is a probability always. This is bit mathematical, bit analytic I have gone into. Yeah. What is the features? Features I said you, the measurable quantities obtained from the patterns. Is it not? Some features can be time variant. Time variant, they can be. Okay. Thumb impression for that sake. It is going to age with the old age of a human. Thumb impressions may change. Okay. With the emotional condition of a person, thumb impression can change. Features can change certainly. They can certainly change. Okay. Generally, numerical mathematical features don't change, but typically biometric features undergo a change, right? Features can be entropy. Entropy of the image can be a feature, right? No, that can happen. But then in Aadhaar card, typically biometric thing, biomedical things, if we derive features from them, they are subject to change with respect to time. That can happen. But features are certainly, they stand for the pattern. They represent object or event or pattern, right? And the classification task is typically based on these feature values. There is lot of stuff, intelligence required in selecting best features. That's the only task rather. And feature is represented in terms of numbers, x1 to xl now, and then represented as a vector, feature vector, x and underline. It could be x bar. It is shown here as underline, some notation, right? And this is now shown as a row matrix, which can be transposed to make a column matrix. That is our convenience. There is a belongingness operator, and it says R raised to L. R stands for real space, real number space. I assume that space surrounding me is comprising of all real numbers. And it is R raised to L. It indicates that it's a L-dimensional real number space. Why L-dimensional? Because my feature vector extends from 1 to L. What will become R2? What is R2 space? Only two features, x1, x2, our typical Cartesian two-dimensional system. If there is only one feature, it is R raised to 1, so only R, real number space, right? As simple as that. It's a mathematical linear algebraic notation, okay? That x belongs to a L-dimensional real number space, real space. All numbers in the real number space are real numbers. I can have complex space also. And the dimensions of this space are L dimensions. We'll be now showing you pictures only 2 dimensions because they are easier for us. I can typically simplistically assume that features are only 2. So it becomes a 2-dimensional feature space. That's the meaning of it, right? So feature space of a typical classification algorithm is, let's say, 2 dimension. Real space 2 dimension. It becomes therefore R2 space. right? That's the meaning of it. Feature vectors are also treated as random vectors. Are they random? I said yes. They are sometimes time variant. Okay, they can change across the scale of time. Therefore, they are random vectors also. Two schools of thought conventionally. Historically, there are two schools of thought. More or less, majority of them lie in our signal processing domain. Okay. Remember again, statistics, probability theory is a sound foundation for all machine learning, even because majority of the pattern recognition classification jobs are statistics or probability theory dependent. Okay. Data is reduced to vectors of numbers, the feature vectors. Data means vectors, submatrices, column or row vectors, right? And probability theory based techniques, statistical techniques are used for the task to be performed. That is statistical pattern recognition. Structural goes more of in a computer science way. Okay, the data incoming feature vector is pictorially represented as a discrete structure. Discrete structure is a some kind of discrete structure in computer science. Okay, we have a course for second year computer engineering graduates, discrete structures and graph theory, some graphical structures, geometrical structures, okay, such as some grammar or graph, and then techniques related to computer science. It doesn't need much sound knowledge of maths. Statistical pattern recognition needs some sound knowledge of probability theory, as I already told you, linear algebra and optimization. Structural pattern recognition may not need that sound depth of maths. Okay, so it is still existing, but anyway, and then we'll be giving example of that also. This is a comprehensive flow chart, which just simply says how many stuff is available in pattern classification, how much rather. Last 2.5 decades is the era of classification, and it is nurturing, further cultivating, right? It is not at all saturating. So two main approaches: statistical approach, structural approach, non-statistical approach. Okay, just go by this side. Non-statistical approach is decision tree. I'm giving example of decision tree to you, or syntactic approach. I'm going to convert the incoming data feature vector into a syntax. Syntax means grammar, is it not? Some syntax, some semantic I try to do, and then decision tree is a graphical structure. I'll be classifying the pattern based on that. Typically, structural approach or non-statistical approach is good for character recognition. Let's say OCR, optical character recognition. Again, believe me, all these techniques are not died. They are still existing. They are not obsolete at all. We still have, in used in OCR or general character recognition, handwritten character recognition, the decision tree and syntactic approach is still used, even though machine learning is there, right? Then coming to the big way, a statistical approach. There are two branches, supervised, unsupervised. We are going to ignore unsupervised branch today. Time is limited. And supervised, we had that Bayesian decision rule, which was very basic, right? Truly probabilistic classifier, Bayesian classifier. And then we have likelihood ratio, decision threshold, all those terms are there. We are going to also exemplify with you a Bayesian, neo-Bayesian classifier. That's a part of my presentation also. There is parameter estimation, maximum likelihood, least square error. Then there is K nearest neighbor, non-parametric kind of learning, supervised learning. This was also quite an old nearest neighbor kind of a classifier. Okay, based on the means of the clusters, means I can decide that incoming vector has some average, some mean value, and simply go for tallying, calculating the Euclidean distance or Euclidean norm or a difference between mean of one cluster and mean of the incoming cluster. Okay, to those clusters the mean is minimum, I'll be classifying that to be nearest neighbor and can have that kind of class that I can do. Okay, K nearest neighbor is a non-parametric learning, typically difficult. Generally, non-parametric kind of supervised classification needs more computations. Okay, so parametric things are typically easier, they require low computations and so on, right? Then we had that unique multi-layer perceptron model, true linear classifier. Even it's a truly derived from AI, and it is now a basic foundation part of machine learning, right? Perceptron. And then truly all neural networks, okay? All RNNs and CNNs. We can go up to deep learning neural networks also, like CNNs, RNNs, all the advancements in that, okay? The back propagation of field, any kind of stuff you can go with. And support vector machine, which is a bit unique in its sense. It is still existing. Believe me, it's still existing, right? All these are still existing. Some are dominating, some are taking backseat, but some other day, some will take a shoot, others will take backseat. That's the way, okay? Nothing here is obsolete. Believe me, nothing here is obsolete. For example, K means clustering, it will never become obsolete. Fisher linear discriminant distance spacing will never become obsolete. right? But all these pattern classification techniques, classifiers, they have got performance metric, performance parameters. Which are they? ROC, receiver operating characteristic kind of a stuff. I can say classification accuracy is how much. I can tell about it. Or I can have a metric like true positive, true negative, false positive, then define accuracy, then define sensitivity. All those parameters I can define, right? And I can have evaluation of performance of all these classifier algorithms over there. I can certainly do that, right? And that can be, there is some learning curve, and then we have gradient descent, which is quite universal now, and local optima, global optima, all those things, local minima, local maxima, all those stuff I can do that. And a lot of things are getting over there. Sometimes dimensionality reduction is part of pattern classification. Feature vectors can grow large in size. And I think some speakers might have talked about it. And I have got then PCA to be a predominantly used uh, machine learning technique for dimensionality reduction. We'll come to that, right? This is by and large universal pattern classification flowchart. And we will be mainly dealing with today this kind of approach, the supervised approach, and we will be mainly dealing with that, right? With many, many examples. How do we do model P of X comma omega, a joint PDF? How will you model that? Typically using a statistical model, right? No, same general classification I'm going to continue with. Assume that this PDF is Gaussian. We have shown two Gaussian things over there. These, by the way, are known as likelihood functions. P, this is a PDF, right? X conditional omega I. Okay, it is PDF of all that population, all those feature vectors, all those feature values with respect to one class, right? What is on the x-axis? All that population, all those feature values are over there, right? Those feature values are assumed to fall in Gaussian PDF. One set of feature values, they are such that majoritarily they'll be belonging to omega 1 class, majoritarily. Okay, that belongs to omega 1 class, male class. And on other Gaussian PDF with its omega 2, which is more or less belonging to this class. These are known as likelihood functions. Okay, and in case of Bayesian classification, I have to see to it that which of them is maximum. P of X oblique omega is maximum, or P of X oblique omega 2 is maximum. Which of the likelihood functions is maximum of the two? Only two classes, omega and omega 2. There are going to be multi classes also over there. Okay, it is as simple as that to make a decision out of these two Gaussian likelihood PDF functions. Which function is maximum? Okay, the function which is maximum, naturally that class wins. Is it not? That's a simple way. So that is, I have to find out this kind of statistical model for it. Okay. What are the challenges? I said no. That is, total presentation is full of concerns and issues. Question marks, therefore. There is a challenge known as intra-class variability. What is that? I have T later over here. T which has been drawn with so many dimensions, 2 dimensions, so much of designs, so much of rich texting, so much of graphics, etc., etc. Right? But all belong to the class T, no? All belongs to class T. But it's a lot of variableness over here. Okay, a lot of variations over there. So it is intra-class, within class variability. They all belong to class of letter known as T. But there are a lot of challenges as far as input features go. Features are different, but the result I want to be T. Challenge. Is it not? Features are this T has got a curvature, this has got so many dimensions, this has got italic, this has got a drawing feature which is now lying. Okay, angles at so many things are different over there. And but even though they all belong to T class, set of features can be challenging. Different. Set of features different. There's an intra-class variability over there. Inter-class variability, 0. This is some license plate, let's say. 0 and D, O and D look same. B8 look same. And classifier is therefore perplexed or puzzled. Is it not? 2 and Z look same. I and 1 look same. This inter-class variability. I have to see to it that this really belongs to class I. Really belongs to class D. These are the challenges with the features themselves. We have to work a lot of the stuff in classifiers on feature polishing. Success of classification with utmost accuracy naturally depends on features. How clean the features are, how separable the features are, how non-redundant the features are. These are the issues actually will be therefore conveying to you. Input pattern, application, pattern class. Just simple application, right? A big chart is given over it, pasted from some resource. Optical OCR is a application, right? Document image is the input. Document image is the input, handwritten, let's say. What are the classes? Characters or words. There can be multiple classes also over there. Okay. Internet search is the application. Text document is the input pattern. Semantic categories. I can view on various semantic categories, right? Email for that sake. Junk email filtering. Junk, non-junk. It is spam or non-spam. That's the classification which I want, right? This is the output. This is input. This is the end application, right? Telephone directory assistance is the application. Let's say speech waveform, spoken words could be the pattern class. Right now, that's the way. I can have A to Z, let's say, or 1 to 9, that kind of spoken words are over there. That can be there, right? Person identification is the application. Face is a biometric input, iris biometric input, fingerprint biometric input. All these are feature inputs, right? I'm going to give the which class? Authorized, unauthorized. Employee of the organization, non-employee of the organization. Okay, authorized user, this is the output class therefore over there. Is it not? Same way, automatic target recognition is an application. So optical or infrared image is the input. So features coming from them and target type again. That's the way. Okay, I'm going to inspect automatically printed circuit board. So intensity or the range image is input. Defective piece of PCB or non-defective. That's kind of intelligence I'm going to imbibe over there. This is just fruit sorting, images taken on conveyor belt, grade of quality of fruit, let's say. And grades can be multiple or two only. Good fruit, bad fruit. That's the way. Okay. So all sorts of real life applications have been jotted down over here. And you know what is a tremendous scope for pattern recognition or pattern classification application. Tremendous scope. Probably only because of classification and regression. I think machine learning became a buzz today. Regression is all about prediction estimations of dependent variables, monsoon prediction. It's a regression problem, is it not? I have to predict monsoon for next year from data of last 200 years, let's say. That becomes a regression problem, had a lot of dimensionality and huge dimensions, a lot of computation complexity, and I can use machine to learn everything, right? Similarly, classification problem has got certainly infinitely large applications. And therefore, you can just note it down. What is the domain and diversity in the applications over there, right? I have to simply classify. One application here, handwritten letter was there, and it has been correctly identified. It was all character recognition over there. Number plate recognition. All fancy plates are there. Not only in India, we have got fancy plates, but everywhere we have got all these license plate, number plates of vehicles, very fancy. And all the numbers are, in case of some surveillance vigilance system, we want to identify the number plate very accurately. Looks simple, but the problem is still universal. Okay, lot of intelligence, AI and machine learning goes behind a simple problem of license plate recognition. Okay, because challenges are tremendous. You can simply look at the diversity and variety of these license plates. Okay, features become complex, classification problem becomes complex. As simple as that. So many colors, so many textures, so many patterns, so many type of styles of letters, and so on. Features complex. I am going to challenge the machine or the human to solve that classification problem. Really challenging, very challenging, right? Biometric, I have already shown this figure, thumb impressions. This something for the eye, something for EEG, something for palm print, something face, something signature. Okay. Again, various challenges are there. All these are typically time variant features. Okay. Biometric features. Then fingerprint, plain arc. These can be all classes. Right loop, tinted arc, pocket wall, plain wall, double loop. All these are patterns over there. Okay. So many kind of stuff I can have the classes over there, right? Face detection, a kind of a surveillance application over there. And this is today even available in our cell phone. Our cell phones are becoming now embedded with a lot of ML applications therein. Okay. And apps can simply locate the faces only. Even the identification classification can be done. Okay. Autonomous drones and vehicles and all, they also have a lot of intelligence over there, and they use classification like anything. Coming to the domain of the FDP, medical applications, there is a skin cancer detection over here, which is written. Okay. And this is some image which has been taken, and a breast cancer. There lies some kind of a pattern over here, and that can be detected, certainly. Okay. This is again a biomedical application. Satellite images are there, or distant images are there, aerial images. We have to simply find out where was greenery, where was drought, where was famine, where was flood. All those can be identified for such remotely sensed images over there. That is there, right? So really tremendously large applications of pattern classification. Today we have recommendation systems, right? Based on my liking, my feelings, which serial, which kind of web series, should be recommended to me or by Amazon or Netflix. A lot of intelligence is there, right? It's also classification. They look at my previous search. They look at all the previous search. They look at, from that they will intelligently conclude, decide that, oh, this person has got this kind of inclination toward this kind of series, and then they will recommend. Okay, targeted advertisement. This is made for this chunk of audience. Okay, spam filters we already said. The emails have to be spammed like spam or non-spam. Loan credit applications, malicious website detection. Everywhere we need classification and the decision based on classification. Good, bad. Typically, many times good, bad. Okay, or multiple classes sometimes that we need many times. I have gone bit hurriedly because all this was probably a common sense to all of you. Okay, there are two phases in pattern classification. One is training or learning phase. Okay, training and learning phase. By the way, machine learning pattern classification typically is statistical problem. Statistics typically believes in law of large numbers. Right now, I cannot say I had a coin with me and I tossed the coin twice. Both the times I got head. So is my conclusion that this coin doesn't have tail? Should I conclude that? No, it is foolish conclusion. Why? Because I did not toss the coin sufficiently large in numbers. Okay. Actually, all probability statistics theory believes that you have ample number of events, ample number of huge amount of data. It is heavy data centric kind of stuff, right? So in training or learning phase, you got huge data samples with me. Features number should be quite large. Data sample number should be quite large. Okay. That in the training or learning phase, I see to it that I got huge chunk of data or features with me. Okay. Or we need that. Then we are going to polish the features. We'll come why discrete processing is required. Okay. Generally, data and features we typically isolate. Okay. This is typical signal processing problem. Therefore, it is prevailing over here. But then typically we have features and then data separate. For machine learning, what is the input is only features. Right? We've got a lot of polished features now, separable features, time invariant features, and so on and so forth. Non-redundant features. These are all properties of features. Okay. I extract features. If I got many features, I select them wisely. Feature selection is a crux for accuracy, classification accuracy. Okay. Wisdom-based selection of features is the only way to get classification accuracy of 100%. Okay. And those features are actually inputs to the model. This model is algorithm. This model is a learning algorithm, right? And these features are input to it, and the model learns them. It model learns, gets trained, and then when in the test phase, when the new from physical environment, a new sample comes, it is acquired, sensed, again polished, again the same feature set is extracted, again the same features are selected, same features, right? There is the same kind of learning algorithm, training, testing algorithm over here. Same model is applied and it gives the decision out. Decision is this class or that class. That's the decision, right? There are two phases, training and testing. Okay, learning and testing. There are two phases over there. All of you know that nicely. Problem taken from Duda's book. There are two types of fishes, fish, sea bass and salmon. There are two fishes. Quality is different, right? Sorting incoming fish on conveyor belt is a problem. There is a camera, conveyor belt is on, and there are fishes coming over there. Images of fish are getting observed. It's an automated inspection system on conveyor belt, right? So we do pre-processing just to have the image enhancement and noise removal and all that. I do that. And then I do feature extraction. Okay, which are the features now? And then classify. There are only two classes, salmon or sea bass. Only two classes over there. Okay, so I have to simply classify incoming from the incoming image, which is inspected by a camera, that this fish is either sea bass or salmon. And see, there is a travel, there is a journey going on. Okay, ongoing, salmon, sea bass, salmon, sea bass, salmon, sea bass. Look, salmon looks gold, sea bass looks silvery. Color is different, right? Length of sea bass is more, length of salmon is less. But you know, length is less. Because conveyor belt, there can be weight sensors also. And people say that sea bass is lengthy, but salmon is weightful. It is not light. Okay. So see, length, weight, color, these can all be features. Is it not? We require sensors also for that. So sensors are required. I require sensor, camera, microphone of speeches, camera for, let's say, images. I require that. And then pattern recognition or classification success depends on resolution, sensitivity, bandwidth, distortion, all of senses naturally. Okay. Therefore, I require a lot of pre-processing. I therefore require a lot of noise removal, image enhancement, etc. I already require to remove all occlusions, etc. Okay. And I find out extract boundary of each fish. All this is pre-processing. Okay. There are two fishes shown over here. So to extract boundaries that I have to do. And then attach training and test data. Training set, test set. Training set is shown here to comprise of only 3 samples. Test set, another 3 samples. Okay. How do we know? A question is posed to you now. Issue is posed to you. How do we know that we have collected an adequately large and representative set of examples for training and testing? Adequately large. Law of large numbers, I say, probability theory needs large numbers. Is it adequately large so that I can really conclude with the confidence, 100% accuracy? Can I do that? And representative set. Representative, remember, all features which I want to extract must be covered in the training phase only. That must have happened initially. Otherwise, if certain new features arise on the fly, then my classification accuracy may be hampered wrongly. It can get hampered, certainly. Okay. So how large the feature set is and whether it is representative, encompassing, it covers all sets of features or not, all types of features or not, that is a big question mark, certainly. How to choose a good set of features? I told you, no, classification businesses for its accuracy, that are all performance metric, depends only on quality of features, how good the features are. Okay. So discriminative features, good features, bad features. See, bad features are seem to be overlapping. Let's say color and texture of an image, mixed many a time. Okay. In a bright color, textures can be easily segmented, identified. In a dull color, they cannot be. Okay. That can be mixture is over there. But the features here are completely discriminable. I have got all those green crosses on one side, all those, there is no overlap at all. So discriminative features. I have to see to it that my incoming pattern has got discriminative features. That is my choice actually. So feature selection goes with the discriminative features. Bad features are overlapping features. I should ignore all of them. Invariant features. Invariant to what? Invariant to time, first of all. Okay. If not, then invariant to geometric transformation, affine transformation, such as translation, shifts, okay, rotation, rotate an angle to an angle, let's say, or scale it up. Okay. They should be invariant features. So say features should be discriminative, features should be invariant. Are there ways to automatically learn which features are best? There is another machine learning algorithm which I can simply put to use which features are best, right? That can be done. Certainly it can be done. Automatically learn which features are best. It is not left to the human or our intelligence or wisdom. It should be left to the machine to do like that. Okay. Some features for characters, let's say. Characters have been shown A, B, 8, O, 1, Y, X, all have been shown over here. Okay. Some dash, some slash, etc., etc. Right? Star. Characters are all shown over there. Area is medium, medium. These are all features. Height is high, high, low. Star and this dash has got low heights, right? No? And whereas slash has got high height. There are some high heights and low heights. Widths, number of holes. Look, this is the striking feature. Which is it? Number of holes in A, only 1. Number of holes in B, 2. Number of holes in 8, 2. Number of holes in O, 1. Quite a striking, separable kind of feature. Similarly, number of strokes. What is number of strokes? A has got 3. 1 is horizontal and 2 are slanting. Okay. B has got only 1 stroke. Stroke is this line over here, right? 8 doesn't have stroke. Everything is curvature over here. 1 has got 1 stroke. Y has got 4 strokes. Okay. So remember, there are number of strokes. All these happen to be features of the character, right? No? How many? 1, 2, 3, 4, 5. Then the center. Okay. Best axis at which angle. Okay. And large inertia, medium, large. These are all the features of the characters which I can use for getting me the character recognized or character classified, right? That's the way. Same example, salmon fish and sea bass fish. Okay. Generally, fisherman tells that sea bass is longer, so length can be a feature. We can use length as a feature. And there is a threshold. Above this length, classified to be salmon. Below this length, classified to be sea bass. That can be done. Certainly can be done. How should we choose the threshold? This is the intelligence, right? How should we choose the threshold of length? so that longer than that particular threshold is probably sea bass, and less than that length is typically salmon. But length can be a feature. Okay. What is the solution? Histogram of length I can draw. Histogram is length, all the lengths are measured and the count is shown. Count means histogram, right? Frequency of occurrence of that much of length is shown over there. And is a threshold shown, L star. Some threshold is shown over there, right? Sea bass typically will be falling in what? Higher lengths. Salmon, lower lengths, right? But there are certain sea bass also which fall below the threshold. So should I classify them to be salmon? It's a misclassification. Classification accuracy is hampered. Is it not some misclassification? So there are some salmon which are of longer length. So should we classify them as correct things? No, they'll be misclassified as sea bass. Is it not? And this misclassification leads to our performance on the accuracy. That happens generally. So histogram cannot be the only way to extract the good features over there. Let's say lightness, weight. Typically, salmon happen to be lower weight, sea bass is a higher weight. Other way around. So sea bass are lighter and salmon are heavier. Again, some threshold has been shown, X star. Okay, but there is again a possibility of misclassification over there. Again, a possibility. So that we have to simply keep in mind that this kind of things will keep on happening. Is it not? That will be there. Multiple features, yes. X1 is lightness, X2 is weight. Two-dimensional feature. So feature vector belongs to now R2. What is R2? A two-dimensional real number space. Okay. X1 is to a real number and they belong to a two-dimensional space. So lightness X1, width X2. Both are shown as a two-dimensional Cartesian space, right? And all the sample points, data points are shown over here, right? No? So every sample point is having two dimensions. Every point means one value of X1, other value of X2. Therefore, every point here corresponds to a two-dimensional data set. Is it not? All data points are 2D data points. One point means two dimensions, two features over there, right? And this length can now keep on increasing. Okay. Larger the length of features means larger the dimensions. Naturally, computational complexity is bigger. They don't require any kind of advice for that, right? No, bigger the length of feature vector, I require more computations to do like that. All data points are of higher dimension, therefore, right? But there is one, to improve recognition accuracy, we might need to use more than one feature. Single features may not yield best performance. Okay, using combinations of features give me better performance. So go for better performance. Okay, better performance, multiple features. Okay, but how many features and which features also matters. How many and which, that also certainly matters. Believe me. Okay, how many also matters a lot. Okay, and is a decision boundary shown. The decision boundary is a classifier algorithm. Wisely choosing this decision boundary, a mathematical equation of this line now, okay, to choose that is a model. That's a model, right? And to wisely choose it, intelligently choose it, so that majority times I get a classification accuracy of 0.99, 99%. So it is an optimization constraint for probability of error or towards getting a classification accuracy equal to 0.99. How to find out this line? Mathematical equation of this line, which is model of the classifier. How to optimize parameters of this line so that classification accuracy becomes maximum. This is optimization problem. It is not simple at all. It is certainly a complex optimization problem as dimension of this feature goes large, right? This is not at all a simple problem. I'm not making you scared. It is not at all a simple problem, but anyway, right? How many features? I said, adding more features always improve performance? No, not at all. It might be difficult and computationally expensive. More features, more computations. Therefore, that is something which is really computationally tough. Correlated features might not improve performance, right? No, correlated features. Okay, I said texture and color are, let's say, correlated. Then I should only consider either texture or color, right? That I should do. So that there is a redundancy of features should not be applicable. Okay, I should see to it that overlapping features, redundant features should be removed. Correlation should be nil. Okay, and therefore features typically in the raw domain, in the time or space domain, are converted to other domain, PCA for that sake. PCA is the other domain, right? Fourier could be other, DWT could be other domain. Okay. And typically when I convert from raw space or time domain to some other domain than time or space, then decorrelation happens. Features get decorrelated. So choice of features in other domain than time or space is always a wise choice. Okay. I may guarantee more classification accuracy if uncorrelated features are selected. Fourier features are more uncorrelated than its original time domain counterpart. Believe me. Okay. So uncorrelated features should be chosen. Always larger number of features doesn't mean good accuracy. And there is a curse of dimension. There's a trade-off. How many features I have to take? It just simply shows that input features m raised to d. D are the dimensions. See, only one feature was there. Two features x1, x2. Three features x1, x2, x3. There are three features over there. Okay. As number of features grow, D is number of features over there. Okay. And each feature is of m dimensions, right? There are m values over there. Then number of training data, learning data grows exponentially with D. Too many features can worsen the performance. Curse of dimensionality. And therefore, dimensionality reduction also goes as an integrated part of every machine learning classification algorithm everywhere. Okay. That happens over there. PCA, somebody must have taken it. Missing features also is an issue due to occlusion. Occlusion is a problem of camera, problem of microphone, right? And some features I may miss. Let's say night vision camera is not there and some night capturable features I may miss. How should we train our classifier for the missing features? How do we do that? That is also is a big challenge, right? And partition the feature space into two regions by finding the decision boundary. How should we find the optimal decision boundary? Whether this line is a correct line, which gives me two classes, salmon and sea bass. All sorts of salmon stuff lies in the right hand side, left hand side. All sort of sea bass stuff lies on right hand side of the line. How to optimally design this line? That is a big problem, right? Decision boundary is not a simple problem. Okay, and then comes complexity of classification model. Model is linear classification model or non-linear classification model. Okay, there is again a trade-off. Non-linear classification model, it is on the right hand side. Non-linear. Seems to be correctly classifying everything. Okay, no misclassification. No here misses. Okay, no, all are hits. All salmon on salmon side, all sea bass on sea bass side. This is here missed, no, something is missed, right? This dot has come on left hand side, it was therefore misclassified as salmon. But because the boundary is now zigzag, it is non-linearly zigzag over there. It is correct classification accuracy, chances are more. But this is overfitting. Believe me. Okay. It is not an optimized solution over there. Complex model may not be the good classification model. Complex models are tuned to particular training set and therefore they'll give best accuracy because see, this curvilinearness, non-linearity is modeled mathematically for a particular training sample class. Okay. Therefore, if the training set is different or the test set is different, then this overfit model may not perform good. Generic model may perform good. A line is simple, no? Only two parameters are there to be estimated. A weight like M and C, the intercept on the slope and the intercept. That's all. Only two things. Here, multiple parameters, many parameters are to be estimated for this model. Okay, so model parameters are more in number, model parameters are less in number. But here the performance for a particular training sample could be 100% accurate. But for other samples, it could be overfitting problem and may not give you the good performance also. This is generic solution. Generic model, simple model, linear model, less number of parameters, less number of computations, only slope and intercept, that's all. It's a linear model. Overfitting model, more number of model parameters, more calculations, more complex model, okay, will be giving you 100% accuracy for a particular class of data. Sample, right? Complex model may not be generic model. So we need a generalization, generic model. Generalization is the ability of classifier to produce correct results on even unseen novel patterns, right? Generalized model we want, and therefore SVM, support vector machine, became popular only because of this, right? All overfitted complex models, more number of parametric models can be accurate but for a typical classes only. It is not generalized. Whereas see, I have just reduced this to this is a higher order nonlinearity. This is only, sorry, this is only a probably a parabolic declination I have shown over there. It's only could be a second order nonlinearity, right? It is simpler model, complex model. Model parameters are large in number and parameter estimation consumes a lot of time. For optimization, this model is tough. Learning rate is a bigger issue over there. Okay, which are the local minima, local maxima, local optima, global optima, tough task. Descending gradients, ascending gradients, tough task. Here, gradient is descending only. So it's a simple kind of model to train. Is it not? Simpler models could be therefore more generic. That may also give you better performance. But believe me, more training examples have to give for simpler models. Okay. So how do we use it? Complex models typically are reserved for a small training set, but a particular training set. Generic models, simpler models are meant for more training examples during training phase. Therefore, they are generic and they assure you good performance for general things, novel patterns also. That's the meaning of it, right? I think you are getting me. There are more 20 minutes with me and 20 more slides. Okay. So I may not be able to finish all of them, but anyway, whatever is good, I'll be able to tell you. Just understanding model complexity. Okay. There is one sine wave shown over there and only samples shown over there. Just enough samples. 10 sample points, just enough. Blue circle, just enough. Okay. They have been shown over there. Now see, there are only one line shown which is going to fit this sine wave and it is not good. M equal to 0. M equal to 1, a slanting line is shown over there. It is again not a good curve fit for this sine wave. M equal to 3. M equal to 3, zeroth order polynomial, first order polynomial, third order polynomial, ninth order polynomial. Okay, this is a simple curve fitting kind of a technique. M equal to 3 is enough, I assume. There are sufficient number of sample points over there. 1, 0 may not be, but 9 is overfitting. Right now, it is not following the sine wave curve at all. So every time going for more higher order polynomial, more number of model parameters doesn't work. There is an optimal number of model parameters, M equal to 3. It just fits over here. Is it not? It just fits. And I'll be getting a good knowledge about this. Okay. Overfitting always doesn't work. Doesn't give you a good result. That's a simple example which I wanted to show you. So 9th order fitted in 1500 sample point doesn't do well. I'll just forget. And people have suggested from the past that when one classifier technique, one classifier algorithm, one linear classification algorithm doesn't give you satisfactory results, it is completely purview of the designer, purview of the implementer to go for concatenation of classifiers. This technique is being used, deployed from last so many years. You have to go for ensembles of classifiers or chain of classifiers, concatenation of classifiers, one after the other, right? What is suggested over there is a pool of classifiers. I can do that, certainly, okay? And then combined classifiers may give you a correct hypothesis tested, correct decision. Null hypothesis or I have to negate the hypothesis or assert the hypothesis, right? Correct class gets identified because of concatenation of multiple classifiers over there. That can be done. This is a well-tested technique of classification that can also be done, okay? What can be cost of misclassification? What cost I have to see? Every misclassification, every error, every probability of error in identifying the correct class gives you have to pay the cost. Is it not? Cost function is an optimization theory terminology. Optimization as a course, as a theory, has got cost function or a risk function. These are two mathematical terms over there. They carry a lot of meaning behind. Okay, I have to pay the cost for misclassification. Okay, what is that cost to be paid? There are two possible classification errors over there. Deciding the fish was a sea bass when it was salmon. I missed it, right? It was sea bass. I missed it. It was deciding sea bass when it was salmon. Deciding fish was salmon when it was bass. Are both errors equally important? No, they are not equally important. Mathematically, they could be equal. Sea bass identified, salmon was desired. Salmon identified, sea bass was desired. But today, in today's advanced technology era, these both errors are not equally important because the choice of the end user enters. Customers who buy salmon will object vigorously if they see sea bass in their cans. Why? Because sea bass is a lightweight, salmon is heavyweight. They went for salmon, they paid the cost, price of salmon, and they'll certainly object if they see sea bass in that. Customers who buy sea bass will not be unhappy if they occasionally see expensive salmon in their cans. Good, no? So see, emotions, feelings, practice, habit of the end user also is taken into account. Does my latest machine learning classification algorithm takes into account this kind of track record, the buying history, the feelings, the choice, the hobby, the habit, the liking of the end customer also? How does this knowledge affect our decision? Great thing, right? And then computational complexity. It is completely my computational platform can take this heavy load or not. Okay, it needs a NVIDIA huge graphic processor and so many servers and so on. My algorithm scale with number of features more, complexity more, number of patterns more, number of features more. Okay, dimensions of features more, naturally computations more, number of output classes to be assigned more. It's not a binary classification problem. More classes, more tough tasks, more competitions, more features, more patterns, more classes, output. So input complex dimensionally, output complex dimensionally. Classification problem requires more computational resources, as logical as that, right? And we need to have trade-offs for all of that. No problem. Is it possible to build a general purpose pattern recognition system? No. Very difficult. I cannot have general purpose pattern recognition system. I cannot have. Very difficult. Why? Because different problems require different features, right? Certainly require different features. Okay. Aadhaar card ID. Okay. It is different feature. Okay. The same image face may not work good when I'm going to send it for the bride or groom selection, because the features are more important there, right? ID card, license ID card or other ID card, okay. I have to simply identify the person as a rough person, rough idea. And this is the fellow, okay? But when the same thing I'm going to judge on the beauty or personality, then I have to really go for a polished face. Is it not? Different problems, different applications require different features. Certainly. Okay. Different features might yield different solutions. Different trade-offs exist for different problems. My priorities could be different. I may not every time want 100% accuracy. I may not want. Okay. My perception of accuracy is different. In Aadhaar card kind of stuff, 90% accuracy is enough. Okay. I'm not going to use Aadhaar card for identifying a person to enter my campus. I got my own thumbprint, thumb recognition, or probably the fingerprint recognition kind of system available to me, right? Thumb impressions are identifying for me. So I may not use that, right? So perspectives are different. So general purpose PR system is not possible. I will be having time, I assume, only for discussing now. There are 10 slides remaining, only for discussing Bayesian decision theory. Very truly classical classifier, conventional traditional classifier, but very wonderful, profound mathematics. As I said you, that if you want to learn, do something in classifiers, do something in regression. Okay, to measure prevailing applications of all AI, MLDL, whatever you learn, two major applications. All of them require lot of profound mathematical knowledge from probability theory, from optimization theory, and from linear algebra. You need that knowledge, much large, right? You don't need integration and differentiation. Those stuff calculus I don't need, but I certainly need linear algebra. If you understand these three mathematical theories, then you can understand any classifiers, right? But again, I say Bayesian decision theory based classifiers are not obsolete. It is classical, certainly classical, right? Feature vectors are random, as I said you, they are variant. Even though I claim that time invariant, transformation invariant, affine transformation invariant, they will not be, right? They keep on varying. So X bar has been, X underline has been shown as X1, X2, X3, XL. There are L, it's a L dimensional feature vector, belongs to RL, L dimensional space. Okay, it's transpose. It was otherwise vertical vector, a column vector. It is now row vector. Assign this based on this feature vector. Assign the pattern represented by vector x underline the most probable of the available class. It's a multi-class problem. Omega 1, omega 2, omega m. A multi-class problem, certainly. It can be binary classification, but only omega 1, omega 2. That is, assign x bar. This is the knowledge to me. It's an input to me. Okay. Assign this to omega I. Omega is one of this 1 to m. Omega is one of the particular classes. Okay. How is it? How do we make this assignment? How x bar is a feature vector. This input is assigned to this omega 1, omega I. How is it? Based on something, a probability, omega I conditional x bar. X bar has occurred. X bar is given as an input to the system. Okay. There is a conditional PDF or conditional probability which I evaluate. Right. This I have to maximize. If let's say this is x bar belongs to omega 1 vis-a-vis omega 2. I have to see to it that P of omega 1 conditional x bar is more than P of omega 2 conditional x bar. Right? This probability I have to maximize, that I have to do, certainly, based on a knowledge of decision threshold. Very, very logical, right? Look at this. There are certain terminologies, a posteriori probability and a priori probabilities. There are two probabilities over there. What is a priori probabilities? There are probabilities of individual classes. I have got a lot of data with me. What is the probability that the data will belong to omega 1 class? It will belong to omega 2 class. This is a priori knowledge. Okay. I have got a lot of theory with me, lot of lookup tables with me, a lot of data from not so many years with me. So I got some profound knowledge about probabilities of every class with me. They are known as a bunch of knowledge for me. Okay. They are known as a priori probabilities. Right. This is the terminology for them. All these class probabilities should be known to me beforehand. Then I got a PDF. Small p is a PDF, capital P is a probability. I should have a priori knowledge of probabilities of all classes. That I should have. This is known as, I already told you, is a likelihood function. Probability that I know the class, and what is the thing? What is the likelihood that this x bar belongs to this class? That's the way I interpret it, right? I know the class omega 1, let's say I is equal to 1. So omega 1, let's say, what is the PDF that my input vector belongs to this class? How much is the likelihood that my incoming vector x bar belongs to class omega I? Therefore, this is known as likelihood function of x bar with respect to omega I. It's a PDF, conditional PDF, which is x bar belonging to this omega I, right? Likelihood function. How much is likelihoodness that my x bar belongs to this omega I? That's the meaning. Okay. Whereas, what is the output I'm interested in? I'm interested in which output? I am interested in the result. What is the result? X bar was occurred to me. X bar was the input, whether it belongs to omega or not. And then I use the Bayesian rule for only two classes over there. It can be deduced. This decision can be calculated, evaluated. What is the decision? Whether my x bar belongs to omega I class or not. The decision can be derived, concluded. It is equal to likelihood function, P x bar omega. This likelihood function is a knowledge. Already I have that. P omega I, a priori probability. Likelihood function, I know beforehand. And P of x bar. What is P of x bar? It is P of all that population of feature vectors, right? How do I calculate that? P x bar equal to, it is P x omega I into P omega I. I equal to 1 to 2 because I assume it's a two-class problem. All the things on the right-hand side have been beforehand estimated. Therefore, I can find out P of omega I x bar, conditional x bar. I can find this out, right? There is something known as a Bayesian classification rule. Look at this. This is the final slide for me. I have to stop after that. So given x bar, only for classes 2, m equal to 2, given x bar classified according to the rule. What is the rule? Probability that omega 1 conditional x bar is greater than probability of omega 2 conditional x bar. Naturally, probability of omega 1 conditional x bar is more than probability of omega 2 conditional x bar. Then naturally x bar belongs to omega 1. Okay, this probability is more. If it is other way around, x bar should belong to omega 2. Only two choices for me, right? Equivalently, we have said it like this. P of omega 1 conditional x bar can be represented as P of this likelihood function, right? I have brought this problem into likelihood function domain. Okay, the posterior probability problem can be defined in terms of likelihood function domain. How was P of omega 1 x bar? It was P x bar condition omega 1 into P of omega 1. If it is greater than the other way, then I'll be getting decision in the favor of omega 1. Okay, otherwise, other to omega 2. If P omega 1 equal to P omega 2 equal to 0.5, both classes are equally probable, then if joint PDF x bar condition omega 1, if it is bigger than a conditional PDF of x bar omega 2, then the result will go, conclusion will go in the favor of omega 1. If joint PDF x condition omega 1 is less than joint conditional PDF x condition omega 2 less than, then decision will go in the favor of omega 2. It is coming to only likelihood functions. See, decision about whether x bar belongs to omega 1 or omega 2 comes to a likelihood function comparison. Is it not? And this knowledge we already have. It has been depicted over here. This is one Gaussian conditional PDF, other Gaussian conditional PDF. Okay, both are a priori knowledge to us. P of x omega 1 is a conditional Gaussian PDF. Omega 1 is the most probable class over here. Okay, all population of x has been shown on the x-axis, and the conditional PDFs are shown on y-axis. They are naturally Gaussian PDFs. Okay, they cut somewhere, intersect somewhere. That is taken as decision boundary. Okay, all x, all feature vectors, all feature values belonging to R1 region should be naturally classified, should be going in, the result will go in favor of Px conditional omega 1. Okay, so below x0 is known as decision threshold or decision boundary. Every x below x0 will naturally fall majoritarily under the area of this likelihood function. Okay, so likelihood will decide in the favor of omega 1. For every x above x0, likelihood goes in the favor of Px condition omega 2. Decision, conclusion, classification is in favor of omega 2. Right? So R1 belongs to decision omega 1, R2 belongs to decision omega 2. That's the way. Okay. So that is the something which we wanted to simply tell. So if x belongs to R1, x underline belongs to R1, x1 will be omega 1. X belongs to R2, x1 will be omega 2. What is the probability that misclassification will happen? Okay, and you can know, anybody can very logically judge. This is the misclassification, is it not? Because the tail of this Gaussian, it overlapped, it lingered in the main area lobe of this conditional period. Okay, whereas this part of this tail lingered into this main lobe. Okay, and therefore this happens to be a gray area. This is misclassification. There are chances of misclassification over here. Accuracy is getting hampered because it's misclassified area over here, right? That's the way. And therefore, we have got this kind of stuff, which is known as probability of error. From minus infinity up to x0, decision goes in the favor of omega 2. We should have gone in favor of omega 1 actually, but it's error probability. So decision going in favor of omega 2, and area is minus infinity to it's omega 1 area. Okay, this is omega 2 area, but decision has gone in the favor of omega 1. So this gives you probability of error. This becomes a now optimization problem. I have to choose decision boundary in such a way that x0 in such a way that this x0 is a decision boundary, right? This to be selected in such a way that this PE becomes minimized. That becomes a optimization problem, right? Bayesian decision theory, Bayesian classifier, which is then modified as Neo-Bayesian classifier, NB classifier, is always looking at minimizing probability of error. Minimization, maximization is always an optimization problem. Therefore, I again said to you that you have to learn optimization theory before you learn classification regression, right? This PE is to be somehow minimized. Is it not? Error probability to be minimized so that I have to total shaded area here. This area is error prone. This area I have to minimize. How can I minimize that? I have to make these regions as separable as possible. After this ends completely, this will start. Okay, that's a clean boundary, clean threshold. But then this region should not overlap. My feature selection should be so wise that this is done. Okay, and therefore this will be pointing towards this PE optimization problem, be pointing towards that wise choice of features, right? That is the way. 55 slides are done, 5 more, but I'll stop here and take some questions if there are, because I have done with my time. Okay, so I should therefore go for some questions if you have.
Yeah, thank you,
Over
sir.
to the organizer.
Yeah, thank you, sir. I request Dr. Tanuja Dope, ma'am, to continue with the question answer session.
Good afternoon, Sutaone sir. From
Yes.
Department of ENTC, I Dr. Tanuja Dupe. There are some couple of questions from the participants. So shall I ask some questions?
Yes, please.
So there is one question regarding in which application can we use for synthetic approach very effectively?
Which approach? Symptomatic approach.
Huh. Yes, sir.
Okay,
Yes.
there is something known as asymptotic. Probably you mean to say asymptotic approach, probably. Okay, because this needs the asymptotic approach is a, I have to ultimately say classifier happens to be a learning algorithm. Okay, in the training or learning phase, I have to see to it that the classifier algorithm is going to get trained or it's going to become learned. Okay, and then in that, I have to choose a model, the classifier model. Classifier model has got something known as the learning rate, right? Then that learning rate value is to be properly chosen and should be driven. And for that, I can use asymptotic approach. Okay, it is probably beyond the scope of this session now because it requires a lot of background to be understood. We'll pass the question. I can answer it offline or on mail.
Okay, sir. The second question is that if I want to go for the K nearest neighbor, okay,
Yes.
whether this K nearest neighbor application will require the computational complexity more if I want to have more and more information, and if it requires a more computation, so what are the effective measures that can be taken so that it will be less computational one?
Nearest neighbor, I told you, it's a simple example is like this, that we have got, let's say, training feature vectors with me. Okay. Many training feature vectors are with me. Then nearest neighbor typically depends on finding out a centroid. Centroid yes. In simple language is average, mean value. Okay. So I got, let's say, 10 feature vectors to be compared. And those 10 feature vectors, for all of them, I got a centroid or the mean average value with me. Right. This goes as an input to the model. I have got 11th new feature vector to me. I'll calculate its mean also, right? That mean, that centroid is now to be compared with the data set. Data set is now for what? I got 10 different centroids or 10 different means with me, which are stored in my model. Okay. So I have to compare them with this 10 stuff. So what is what is value of K therefore? 10 here. And then 10 Euclidean distances I have to find out because there were 10 average values or 10 centroids with me, right? The accuracy depends on what was my training data set dimension. If I said 10, no, here, so it could be 100 also. And naturally, what generally happens is that if I want more accuracy, training should be rigorous. So I should then use naturally more number of training feature vectors. Then the accuracy will be better, naturally. Okay, but it asks for more computations. Naturally, it is but natural. The K value is larger, it will ask for more computations.
Okay, thank you, sir. And there is one more question. Right now, there are lots of data sets are available for training and testing. So, which is the best data set that can be used for training our model? If we go for K nearest SVM, and there are number of classifiers are also there.
Yes.
So, because
so
different data set, they are having their own, you can say the number of images, for example. So if I want to check the accuracy of my classifier, so which will be the most suitable data set which we can be using it for experimentation purpose?
Got it. So I said, classification success, it all depends on the types of features, right? How clean the features are. So you should naturally choose that data set which has got clean features. I don't need much of pre-processing, right? They're already quite processed, they're quite polished. And all the features which you are going to use for classification, those features are clearly visible. Okay, clearly quantified. and the features vectors are as good as noise free. They are not affected by any of the sensors and any noise. They are typically enhanced. Let's say if there are images, they're all enhanced, all noise removed, all low pass filtered, and the features which you want to use for training purpose, those all features should be cleanly visible, available to you, transparently available to you. Then go for such features. And the success of class naturally depends on the types of features you have. The data set should be clean in all respect. Typically, we recommend to go for validated data sets. There are some validated data sets which have got all the polishing, all the enhancement already done. Pre-processing is already done. So better go for pre-processed data sets or validated data sets. Don't go for any raw data sets.
Okay.
That's the recommendation.
There is one more question. In broad data texture image, if patches are cropped closely of size 48 by 48 in that texture image, then which features can be used to identify those cropped patches?
Oh, the size is big, no? Then the pattern of textures. See, textures is really very complex problem actually, because there are many types of textures available. Okay, semi-random and truly random and then structural. All those things are available. If the patterns are, see, mean the basic building block, texture basic building block structure is quite big. It encompasses, let's say, 10 by 10 pixel block. Then go for bigger size of the pattern, right? If the texture, the texels, as people say, if the texels are very refined, they occupy only, let's say, 2 by 2 pixel window, then you have to naturally go for the other kinds of pattern recognition technique, right? Textures is typically a very complex phenomenon.
Okay. With this, all questions has been thoroughly and in detail answered, sir. Thanks a lot. So now it's
Sir,
so
Jadhav sir, बोला. काय
sir,
म्हणताय?
good afternoon, sir. BD Jadhav
Good
here.
afternoon. Yes.
Thank you very much. तुमचा valuable time दिला त्याबद्दल.
नाही, काही issue नाही.
Thank you very much.
Yes.
And
Only
very
I
nice
said that,
session.
no?
I have one meeting with the management, so I could not attend all. But
No, anyway, not
so
required.
initially I have not joined.
Yes.
Thank you very much, sir.
Yes. Thank you. Yes, thank you.
Madam, please continue.
So should I leave the meeting,
okay,
madam?
Sir, just wait for 1 minute, sir. From Department of ENTC, Rajarshi Shahu College of Engineering, I, Dr. Tanuja Dope, I am very much thankful to Dr. Sutaone, sir, for sparing your valuable time to deliver expert talk on pattern recognition, classification, or cursory review concerns and issues. You have nicely given, you can say, the basics of what is MIL, what are the various classifiers involved, and the specifically to me, I like your application which is related to the classification of the fishes. So thanks a lot, sir.
Thank you.
Over
With
to
the feedback of the audience, right? If you are taking the written feedback, then you can just share it with me.
Yes, sir.
Yes,
We'll share
yes,
the
sir,
feedback.
definitely.
Yes.
Sir, I will call you. Sir, I will call you.
Yes. Okay.
We are meeting on 4th, sir.
Yes. I remember that. Yes, we'll do that.
Okay, thank you, sir. Thank you.
Thank you.
Okay, participants are informed to join the next session at 2 p.m. Thank you.